Hey YouTube, I want to go over the drawing of Manfred's ESR meter, kind of explain what's going on with it, and then here in a little bit I'll show you the mods that I made to it. I built one originally, tested it out with an external amp meter, and it worked so well and so handy I decided just to go ahead and put one into an analog volt-ohm meter. I'll show you the one that I built here in a minute too. It works really well. Anyway, the basics of Manfred's design. I also want to thank Manfred for sharing this with the world. It's really a nice little meter. You can't beat it, and you can build it from parts just laying around. I have mine powered with just a 9-volt battery. It's going through a 5-volt regulator. I used a 78 LO5. You can use whichever 5-volt regulator you wish. This is just a little 100 milliamp regulator I had laying around, and that's more enough power than what this meter needs to run. He has the first op-amp set up as a square wave generator. It puts out about a 4.8 volt peak-to-peak signal at around 50 kilohertz. Mine was a little bit faster. Might have been around 70 kilohertz is what I got. It's just the tolerance on the caps and the resistors. But anyway, it's coupled with a 10 mic resistor or 10 mic capacitor, and then that's stepped down to about 250 millivolt peak-to-peak signal by this 20-to-1 transformer. The transformer is necessary to provide low impedance and isolation, so you can measure these low-value caps. He has a 10 ohm resistor here at R5 installed across the secondaries. He has it set up so it absorbs any inductive spikes that may be produced by the transformer. The return signal from lead 2 is attenuated by the 10 ohm resistor to ground and coupled by the 10 mic capacitor at C3. Signal then is amplified by the second half of the op-amp, rectified, and then output to the 50 microamp meter. R11 is a 100K trim pot. That's used to calibrate the full scale reading on this meter. Okay, here's a schematic I made of the modifications I made to Manfred's original designs. Start off with, instead of the TL062 op-amp that Manfred used, I used a TLV 272C. This is a low voltage CMOS rail-to-rail op-amp. I had a couple dozen of these left over from a grab bag that I got from Jameco, and pretty nice little op-amps. Low offset, very nice, very nice. Anyway, the second mod was in order to control the frequency of the square wave output of the first op-amp, I installed a 560 picofarad capacitor down at C1, and then I installed a 200K trim pot at R4 that I can adjust, and by adjusting the resistance on this pot allows me to select a frequency of which I wish it to run at. Most of the ESR meters that you can buy are set to run at 100K. With mine, the way I have it set up right now, it maxes out around 1 megahertz. I can't ever see needing to test anything that fast, but I can if I wish. And all the way down to about 50 kilohertz as originally designed. The second was the transformer that I used. I found that Radio Shack has an audio output transformer that'll work very nicely here. Part number again is 273-1380. This was hanging on a shelf at my local Radio Shack. So it was $2.99. So it was real reasonable, and that way I didn't have to mess around with building my own or finding one with the step down that I needed to do to get this output of this transformer back down to around 200 millivolts, so you can test your capacitors in circuit if you wish. Highly recommend the Radio Shack output transformer. And then at R6 I installed a 20K pot. This just at higher frequency levels, this allowed me to attenuate the signal coming back out of test lead 2 from the capacitor. This also allowed me to span the meter so I had better resolution. Before, I'll show you in the demo of the meter, I only had a deflection of 1/10 of an inch that coincided with about 1 ohm's resistance. And by trimming this pot out to attenuate that signal a bit, it kept this op amp from saturating so easily, and I was able to get better definition out of the signal. This attenuation obviously has to change with the frequency output of your first op amp. You do have a lot of loss going through this little audio output transformer once you get around above a couple hundred kilohertz. At 1 megahertz I had to attenuate the signal all the way down almost to the full scale to about 20 ohms in order to get a good enough signal back to amplify by this op amp. I know I could have gone ahead and put a potentiometer here on the inverting output and increase the gain of this op amp, but I didn't really want to have to put another pot in here to tweak either, so I just left the gain on the op amp alone, and I just attenuated a signal with the 20 ohm pot. It works good. And I stuffed it all inside of a cheap little analog voltometer, a little Gardner Bender GM318. Found this one out at Menards. It was $11.99 is what I paid for it. So the parts I had to purchase for this total were $14, and then that way it stuffed it all in that nice little box. It wasn't an easy fit. I had to mod it quite a bit, and I'll show you that here in a little bit. But it all works great, and I'm really pleased with it. Okay, I have my first meter set up here. This is the first meter that I built off of Manfred's design. It was a pretty quick, rough build. I just junked it, dead bug design, chunked it together, threw it in a jiffy box. This output knob's on and off, and it also adjusts R11. That's R11 on a schematic. I have a little cheesy volt ohm meter here, but the nice thing about it it has a 0.5 milliamp scale on it, so that allows me to use it with this homemade meter. It's 2-piece, and it was kind of a pain. That's what prompted me to build a new one. Let me hook this up here, and then these are the capacitor test leads. Short those out, and that's what you have to do to calibrate the full span of the meter. So we'll turn it on here, and we'll adjust R11 here, and span it out, and zero that meter out. It may not be exactly on 0 from your perspective, the camera's perspective, but best I can see, that's 0 right there. On the board behind it here, I have the some test resistors. Set this off to the side here where I can reach them. And this is 1 ohm resistance on the original meter that I built. You can see the deflection. It's just right at that first tick on the top scale. 1 ohm. 2.2 ohms. Just a little bit above 2 ticks. As you can see, if you had to test the ESR value of a capacitor down to 0.5 or even 0.2 ohms, it'd be a little difficult. That's 4.7 ohms. And here's 10 ohms. So even at 10 ohms, I'm not at 50% of the scale of the meter. It definitely needs to be spanned out. Yeah, I could have gone in there and tweaked the original board that I had everything built on, put some pots in there to let me adjust stuff to span it out. But it was a two-piece meter. It wasn't really convenient for me to use, so I thought, well, I think I'll just go ahead and leave this one alone, and I can use it to check the impedance on speakers, or I can use it to check smaller transformers, anything to where I actually need an ACO meter. It works good for that. So I didn't really want to change it, so I thought I'd just go out and build a new one. And here I have my original meter that I built hooked up to my oscilloscope. And I'll swing it around up here so you guys can see the waveform on it while I've got everything set up. And as you can see, the scales are both the same. 356 millivolts peak to peak. And why that's higher than Manfred's original design is because that I used that Radio Shack audio amplifier, and it doesn't quite step down the voltage as much as the 20-to-1 ratio that Manfred had designed. This is probably closer to 11-to-1, I would assume, since the output of the oscillator is running about 4.8 volts peak to peak. It's more than 10-to-1, but it's definitely not the 20-to-1 to get it down to that 200 millivolts. And of course I could attenuate the signal coming off of there with a voltage divider, I suppose, if I really wanted to, but it works good enough for me the way it is. We'll note that this is a fixed frequency as designed by Manfred to begin with, and as it shows there, it's actually running at 55K, which is really close to the design that he had originally put into his drawing there. So anyway, I just wanted to show you that to you. And here's a new meter that I built. I crammed it all inside a little bit larger analog volt ohm meter that I bought out at Menards. Definitely was just big enough to get everything in there easy. Have an on-off toggle switch that I put on top. Removed the original center selector switch, and then I put the scale for the ESR scale on the front of it here, as you can see. And to zero this one out, I have my two probes here to the meter. Just connect them together and zero it out with this little pot right here. This is the fine trim for R11. I actually have two pots in there now. I didn't show that on the schematic, but that was kind of a in situ mod that I made after I had everything put together. I thought, well, I'll just go ahead and leave this pot on there, this fine trim. It's a 1000K pot. Okay, so I got that all trimmed out nice there. And I'll show you the deflection on this meter. Okay, here's 1 ohm. As you can see, it's right at 1 on the top scale. Here's my 2.2 ohms resistor. That's reading about 2.6 on that top scale. It's a 4.7 ohm, and that's reading just past 10. And then on my 10 ohm resistor, if you can see it, it's reading just right at 100. There's just a bit of meter reflection there. You can see I removed that and I hooked it back up there, and And that's what I was shooting for when I originally spanned the meter, was full deflection to 10 ohms. That gives me plenty of increments in there to be able to read the meter. Okay, I just wanted to go over a couple real life demos on some of these capacitors. This is a bad 1000 mic 16 volt cap. This is one I pulled out of that Action Tech DSL modem. And again, this is the full scale. Let me calibrate this now that since I changed the frequency a little bit. I messed with frequency. I'm going to have to recalibrate the span of the meter. Not the span, but the full range. Okay. And here's the bad ESR meter. So you can see that's way back, 10% of the deflection of the meter. So that's at 5 ohms resistance roughly. Here's a 1000 mic 16 volt. It's good. This will show you in comparison. This is a good one, and it's reading clear down there. It's about 1/10 of an ohm, 100 milliohms. This is another bad capacitor I took out of that Action Tech. It's a 330 mic 6.3 volt cap, and it just deflects the meter just a little bit, and that is all. It's reading roughly 500 on that top scale. A 330, according to my scale here, a 330 mic should read at 16 volts, should read roughly 0.25 ohms. I've got a brand new 330 6.3 volt here, and you can see right down there we're just right at that point, 0.2 0.3 ohms. Here's a used 330 6.3 volt, and it also measures about the same, about 0.2 0.3. Here's a 220 volt or 220 mic 10 volt, and it's reading at 0.2 or about 0.3, and that's what it should read. It's a 220 mic 16 volt, or a 10 volt actually, so that can go all the way up to about 0.8, so we're in good shape there. And finally, here's a 470 mic 16 volt used cap, and the 470 should read at 16 volts about 0.18, and it does real well. It's right at that point, just below 0.2. So just show you that you're able to read those real small values on these real small ESR values on these caps with my new meter a lot easier. Okay, I want to go over some of the features of that I put into the new one. Like I said before, this is the R11 pot fine tuning. If you look on the back of it now, this is R11 down here. This is a coarse trim. Down here is R6, the pot I put in there to attenuate the signal, so I could actually, this is how I span the meter, is by attenuating that signal. And on top again, here's my on-off switch, and right here there's a 10-turn precision pot. That's R4. This adjusts the frequency of the square wave generator on that first op amp. I'll set this up and I'll show you guys the frequency and the voltage on this on my oscilloscope. Okay, I have the test probes on my new meter set up. with my oscilloscope so you can see the frequency it's operating at. Right here we're running right at about 100 kilohertz. I've read that is where the capacitors are the most reactive, the most resistive. Have my division set at 100 millivolt divisions. So right now the probes are set running. They're a little bit hotter than the design. This is where I get my best span and function. It's running at 350 millivolts peak to peak. And then, as I showed you, I have an R4. It's on schematic, that 10-turn precision pot. I can vary the frequency of the meter. So if I wanted to test it at a lower frequency, I can take it down to close to 10. I want to measure it at 10 kilohertz. I can definitely do that. And then it will scale all the way up to over a megahertz if you wish to run it that hard, just by adjusting a pot. It does quite a bit of loss in the transformer when you run it that quick. It gets real noisy. But anyway, even at 1.6, 1.7 megahertz, I'm at 48 volts peak to peak. I definitely have to adjust the attenuation on my my probe there in order for it to be amplified by that second op amp enough to be able to measure it on my meter. But it is fully adjustable. A little kind of a pain. You can dial it back in anywhere from 1.5 megahertz all the way down to 10 kilohertz. Just set it back here to around 100 kilohertz. That 10 turn precision pot makes it real easy to do that. Okay, I thought I'd go ahead and open this meter up so you can look and see how I fitted everything in there. It wasn't easy, but it did fit. Okay, point a few things out. My on-off switch, I just epoxied that in there, and again with my R4, the frequency control pot, I just used some plastic epoxy and epoxied that in there and put a little hole so I could adjust it, run the wires over to the board. Down here, this is R6. This is the attenuation pot. Attenuates the signal coming back from the capacitor being measured. This is R11. This is what you adjust. This is the coarse adjustment on R11 for the full meter swing of your scale. This is the fine adjustment pot, R11, where you just tweak it very minutely. This is my op amp. And over here is my 78L05 voltage reg. This is the audio output transformer that I purchased from Radio Shack. It works really nice. And the battery, you can see that when I originally built this, I took the board out, and I took all the components off of the board, removed the switch, patched up that hole, put the scale in front of it, notched out a big chunk in the circuit board, got my battery to fit first. That was the very first thing I did. And then I started placing my components wherever I could, where they would fit, and everything kind of flowed together. And it works great. And again, I can't thank Manfred enough for sharing his design. Go build one.